Let's check for sound first, as per usual. Audio sounds okay. Let's check for video. And that's also looking good. Time to put away the headphones and get started. Alright, so I had to postpone this multiple times, just like the previous stream, as some of you may have noticed, but better late than never, I suppose, and technically we are ahead with the extra streams that I did manage to squeeze in over the past several weeks. So yeah, not too worried. We've only got, half of the current chapter, and then 2 more chapters left to go for the Physics 1 students, and then for the Physics C students, it's what's left of this chapter, and then the next chapter, and then some calculus-based revisits to previous topics, which I'll probably be able to go over in, I want to say maybe 3-4 streams. We'll see. Let me think. Other things to announce before we get started today. So while checking and timestamping the previous stream, I noticed that YouTube has started putting ads on my videos. I did not choose that. That's just something that YouTube decided they would be doing since late 2020. Somewhere around that time, they'll put ads on channels that don't even meet the requirements for their partnership program. I'm not particularly interested in the partnership program, but if they're going to put ads on my stuff anyway, then I might as well get my cut when and if I reach the eligibility requirements. But I would honestly prefer to just have the option to tell YouTube, hey, I don't want ads interrupting my lessons. They used to do that. They used to have, there were some, brand channels that could specifically request to not have ads put on them because, if your channel is for a business and you don't want ads for your competitors appearing on your own videos, that kind of makes sense. I don't know if they still have some remnant of that policy that I just don't have access to, but I'll do some digging around and see if I can just disable the ads outright, which I probably can't. Then that is what I will do. If not, then I guess we'll just have to deal with it. So sorry for those of you who are frustrated by that stuff interrupting you. I was certainly frustrated by it because it was constantly while I was trying to rewatch the stream to timestamp it to figure out what the best times to put in the chapter links were. It just made the whole process more frustrating. But anyway, today's topic, we're digging deeper into center of mass and moment of inertia. I touched on them a little bit last time, and today I want to go over some more intuition involving them, especially moment of inertia. We're going to be doing some more calculations involving that. And yeah, I think it's going to be a very intuition-heavy stream today. There's going to be a lot of stuff that I just want you to kind of develop a sense and an intuition for, even if it's not necessarily something that they're going to explicitly ask you to do on a problem, even if there's no actual, writing down calculations and problem solving involved. I think it'll help with setting up problems in the future if you have this kind of intuition for these two concepts. And towards the end, depending on how much time we have left on the clock, not that I have a set amount of time, but I would like to try and keep it to around 3.5 hours at most, because my goodness, last time went for 4.5, and I wasn't expecting it to go that long, and the way I felt by the end, I don't know, I guess I just don't have the stamina that I used to back when I recorded that one 7-hour long chemistry video in one go. Or maybe it was because I recorded that day after doing a lot of other work prior, so I wasn't at full energy when I started. But yeah, so let's begin with homework questions from last time. I left one for the Physics 1 students and another one for the Physics C students, and the one that I left for the Physics C students, you're still going to want to pay attention to it if you did Physics 1, or if you're in Physics 1 rather, because while the process is not necessarily something that you're required to know, the conclusion of it, based on a free response question that I saw on an AP Physics 1 exam, the conclusion is something that I believe they do expect you to know. I wish they would communicate that more clearly in their course and exam description, but okay. Better to be over-prepared than under-prepared, I suppose. So let's begin with the Physics 1 question that I asked, which was... where did I leave it? Ah, here it is. No, wait, that's not it. Where is it? Oh, wait. It was right in front of me and I missed it. This one. And I guess because I'm not used to streaming this early in the day, I didn't account for the fact that there's a bit of sunlight coming in through my window. Hopefully that won't annoy too many people. Should be going away soon enough. Anyway, so the question was, we have two pegs supporting a wooden plank. There's a person who starts halfway between the two pegs. The two pegs are 1.75 meters apart. The person has a mass of 65 kilograms, and the plank has a mass of 20 kilograms. And the question was, as this person starts walking, how far do they walk before this wooden plank or beam or whatever you want to call it begins to tip over, and what is the force in this peg over here when that happens? That is the question. So backside of this is available to work on. I guess we will use it. I'll redraw the diagram. Make sure everything is in frame. So we have this beam, or plank, or whatever you want to call it. Full length is 4 meters. It's supported by two pegs, which are 1.75 meters apart, so I'll draw the second one over here. The person starts at the halfway point over here and starts walking some distance x along the beam. They start at the halfway point between the two pegs, so half of 1.75, whatever that is. Let's see, it would be half of 1.5 is 0.75, and then 0.875 meters, if I'm not mistaken. Might as well double check with the calculator. 0.875 times 2 is 1.75. Okay, I guessed correctly. And we've got forces from those two pegs. There's going to be a force from this one, which I'm going to call force right, and a force from this one, which I'm going to call force left. And the board is loose. It's not nailed down or anything to these pegs. So the pegs can't really pull on this wooden board. And then the board itself is going to have some sort of weight to it. So there's going to be a force of gravity here. My vectors are not going to be drawn to scale. This person is going to have, let me do it in a different color. This person is going to have a normal force pushing up on them to counteract their weight, which pulls down on them. I guess I'll call it force gravity person. And now I haven't left enough room for drawing the normal force that the person exerts on the beam. Fine, we'll just draw it through there. Yeah, there's the reaction to that normal force. I probably should have at least drawn the normal forces with equal scaling, but we gotta do what we gotta do. And that should be everything. So let's start with, even though it didn't really ask this question, let's start with figuring out what the forces are in the two pegs in the beginning, before this person starts walking, just for the sake of getting some sort of sense of what's going on here, just for the sake of having something to compare our results to after we see them start walking. So I would say that this system is in static equilibrium at first. So I can just place my pivot anywhere I want, and I will place the pivot right over here, where the left peg is. So in that case, net force X is going to be 0. Well, there are no horizontal forces, fortunately, so we don't have to do anything with that. Net force in the Y needs to be 0, so we need forces upward minus forces downward to be 0, force left, plus force right, minus, I was about to write a plus there, minus normal force and minus force of gravity on the board must be equal to 0. I can go ahead and calculate what those two forces are. The board was 20 kilograms and the person was 65. Yeah, 20 and 65. So we've got 20 times 9.8 should be 196, and 65 times 9.8 is 637. So we've got 0 equals force left plus force right minus 637 and minus 196. We know that the normal force is just equal to the weight of this person because this person is supposed to have a net force y of 0 as well, so whatever normal force acting upward on them must equal the gravitational force pulling them down. Probably something you've heard too many times by now, but I'll repeat it anyway. And I might as well go ahead and add these over to the left. So that's going to be 637 plus 196 is 833. So 833 equals force left plus force right. Okay. Now I want to write my net torque equation. So net torque needs to be 0 for any and all pivots. Since this thing is already stable, then it must already not have a single pivot around which the net torque is non-zero. So I can pick whatever pivot I want. We already chose the far left end. So starting from the left and working my way to the right, I see torque due to force left. That's going to be 0 because it's at 0 distance, times force left, times, it would have been 90 degrees, I suppose. And then next force we encounter is the normal force downward. That's going to cause a clockwise rotation. I'm going to go ahead and say clockwise is the positive direction for this problem. I'm going to go ahead and choose clockwise to be my positive direction. So this will be plus, and then it's at a distance of 0.875 from the pivot, or displacement rather, of 0.875 is where that force is being applied, times, it was 637, times sine of 90 degrees, sine of 90 being equal to 1. Might as well slash this out as well and call it 0. Okay, next up we've got, as I continue moving, next thing I encounter is force right over here. That's going to be at 1.75 meters away from my chosen pivot. And that's going to cause a counterclockwise torque. So I'm going to call that a negative 1.75 times force right. I guess I don't really need the parentheses here, but you know, times sine of, it's going to be at 90 degrees, right? Pivotal displacement is that way, and the force is up. They make a 90-degree angle with each other. And then force of gravity should be acting at the center of mass. The force of gravity on the board itself should be acting at the center of mass of the board. Since the board is 4 meters long, then this must be 2 meters away from either end. So it's going to be 2 meters away from the pivot that I've placed on my left end. And it's going to cause a clockwise torque. Clockwise, we decided was positive here. So positive 2 meters times 196 times, it'll be at 90 degrees between the force direction and the pivotal displacement direction. And in case that word is foreign to you, that is the word that I came up with in the previous stream for the displacement from the pivot to the point that the force is applied on an object. I called that pivotal displacement. Patent pending. Not an official term, but that's what I'm going to call it. Maybe it is an official term. I forgot to try and look it up and see if maybe somebody already was using it before me, which is not too unlikely. But anyway, so this all needs to add up to 0. So let's go ahead and see. We can solve for the only unknown left here is going to be force right. So we're going to get, let me switch colors. I'm going to add since this is the only negative term here, I'm going to add it to the side with the 0. So 0.875 times 637 is 557.375. 557.375. That's a very weird looking 5 I wrote there. And then plus 2 times 196. So that's plus 392. And that's supposed to equal 1.75 force right. And if I go ahead and add those two numbers and divide, 557.375 plus 392 is 949.375, and divide by 1.75. Oh, how nice. It's exactly 542.5. I was expecting some ugly decimals, but I'll take this. 542.5 newtons. And then we can use this to figure out force left. If we just go back up to here, that would probably be the easiest way, although if you really insisted, you could just write another net torque equation instead. So 542.5 minus 637 and minus 196. 542.5 minus 637 and minus 196 is negative 290.5. So I get 0 equals force left minus 290.5. Therefore, force left must be 290.5 newtons. Okay, so that's going to give us some sense of, or some sort of basis of comparison. So as this person walks closer and closer to this peg, they're going to be shifting more of their weight, or rather the normal force they exert on the board as a consequence of their weight. So I'm going to expect to see FR is going to increase from 542.5 to something else, and FL, force left, is going to decrease. So back when I first encountered this problem, I couldn't come up with anything. I was kind of just going around in circles, generating multiple net torque equations, hoping that I could find something. I had 3 unknowns to work with. I had my unknown x, my unknown force right, and my unknown force left. And no matter what I could do, because I don't have anything with net force x here, I only had 2 equations to work with. No matter how many times, no matter how many pivots I chose for my net torque, and how many net torque equations I wrote for each of those pivots, I would just be going around in circles, getting nowhere, because I failed to realize something important that happens when the board is about to tip over. If the board is about to tip over once this person walks a sufficient distance, then it's going to tip over around this point. So this point is going to be the pivot. And the other more important thing, is that force left would have to go to 0, because if the board is about to lift off, if it's about to lose contact with this bottom peg, then there shouldn't be any more force between the board and this peg on the left. So force left, you can conclude, if the board is about to tip over, then force left must be 0, and that brings it down to 2 unknowns, and from there you should be able to solve the problem. So let's go ahead and write our equations. and see what happens in this new scenario. So, new scenario, we're going to have pretty much remove the peg on the left from the problem. And I don't have to pick this as the pivot necessarily. If it's just about to tip over, then it's still in equilibrium. So I could still freely choose whatever pivot point I want, but I think I'm just going to go with this. It's probably going to end up being the easiest to use. So I'm going to redraw this. I'll keep, let's see, did I keep it lined up nicely? For the most part. Okay, then I'm just going to keep using these. I'm not going to rewrite them down here. So we've got that peg down there, and then it's going to be exerting some force upward. And then there's the force of gravity on the board, exerting some force downward. So we've got, if we choose this as the pivot though, then the torque from force right, the force from the peg, its torque is going to be 0, which means that the only other force that we're going to have, the normal force exerted by the person, it has to be somewhere on this side. So this person doesn't even move past that second peg. The person is still standing somewhere around here. So that's the person's starting point, and they're going to walk to somewhere around here. We don't know how far yet, but they're going to walk to somewhere around here, and they're going to, I probably should have drawn this in a different color. And whatever normal force they're exerting, it's going to have to be somewhere on this side so that you can get a counterclockwise torque to cancel with the clockwise torque from the force of gravity. Okay. So we need to, I guess, calculate new distances. If this is the 2 meter mark, and if this starts off as 0.875 meters away from that second peg, then we can, let's see. Oh, and I guess we need to use that 1.75 as well. So 2 meters minus 1.75, this distance, this gap over here, has to be 0.25 meters. I'll draw it over here. 0.25 meters. So we're going to use that for the pivotal displacement for force of gravity, and then for the normal force, it's going to be 0.875 minus x, whatever x is. It's going to have to be 0.875 minus x. This distance over here, whatever it is, it's going to be 0.875 minus x. So let's go ahead and write for our net force equations. I guess force right is already predetermined, because if you reduce this to 0, I'm just going to copy this over. We get 0 equals force left, which is 0 in this scenario, plus force right, minus the 637, and minus the 196. So force right we can already figure out without having to do the net torque part of it. And then net torque equaling 0 requires, I'm going to continue with clockwise being positive, so I'll write the torque due to gravity first. That's going to be 196 times 0.25. So 0.25 times 196 times sine of 90 degrees. And then that's going to be our counterclockwise torque, which for this problem we've decided is negative. It's going to be 0.875 minus x times the normal force was 637 times sine of 90 degrees. Okay, and the rest is just algebra. So let's add this over to the left-hand side. We get 0.875 minus x all times 637 equals 0.25 times 196. That's going to be what? Half of 196 is 98, and then that means a quarter would be 49. And then divide by 637 so we don't have to distribute. 49 over 637 minus 0.875. 49 over 637 minus 0.875 is negative 0.798. So negative x equals negative 0.798 meters. So cancel the negatives on both sides, and there you go. X is equal to 0.798 meters. Pretty good distance. This person gets pretty close to the second peg. .798 from 0.875, if I go ahead and subtract that, I get 0.077. .077, so that's within about 8 centimeters of that second peg. I could give you another problem which is basically the same thing, except make these make the distance between these greater than half the length of the board. And you would see then that the person would actually have to move past the second peg in order for that tip over point to happen. So if you would like to do that, just take this problem and modify it. Take this 1.75 and instead just, I guess, invert the problem. Tell you what, the easiest way to do this would be take this peg on the left and just move it over to here, and then take this person and have them stand on this side and make them walk to the left instead. That would probably be the easiest way to redraw the diagram if you want to do that other scenario. Another thing you could do is just keep the same drawing, but maybe adjust the spacing a little bit. And instead of 1.75 here, make it, I guess it would be 2.25, and then 1.75 meters would be the amount that's left sticking out after that second peg. So yeah, you could modify this problem if you want to explore this idea a little bit further and see what happens in the scenario where the tip over point requires the person to move past the peg. And perhaps you could even do a calculation to figure out where do the pegs need to be placed. At what point does it switch from the person being on the verge of tipping the thing over. Oh, wait a minute. Actually, hold on. If the peg is about to... Which way would it tip over if the person moved any further? It would have to tip over clockwise, right? Because if this person moves any further than 0.798, then this number is going to get smaller, which means you're subtracting less from this torque, and this torque overall is clockwise. Okay, yeah, it would tip over in a clockwise direction. For a minute there, I thought I messed up the problem. Forget what I was about to say. I almost was going to say that this would have meant that it would tip over backwards, which would then necessarily mean there's going to be a force in the peg on the left, but no, I was thinking about it the wrong way. Let me think here. There was something else I forgot to say here. What was it? What am I forgetting? What am I forgetting? Oh, I guess we can, go ahead and calculate force right over here. Just 637 plus 196, which I guess we already had earlier as 833. So yeah, force right is just going to be 833, which is higher than the 542.5 that we got before. So it checks out with our intuition that moving closer to the peg shifts more of this person's normal force on the board onto that peg. That all makes sense. Anything else I want to say about this problem before I move on? Well, in case I didn't finish describing it, something that you might want to look into if you decide to do the second scenario of this is at what point do you get the difference between, what's the reason, I guess, is what I'm asking you to try and figure out. And some of you might already be able to see it, but for those who don't see it immediately, what is the reason why the tip over point happens before the person crosses over the second peg in this scenario versus after in the other scenario? What is the reason? What is the, I guess, dividing line between the two scenarios? That's a conceptual question for you to figure out on your own. You might be able to figure it out without doing any serious math, just drawing some stuff. But if you need to do some math to figure it out, that's fine. Okay, now we can move on to the second question. Wow, it's already been 40 minutes. So, second question that I left for the Physics C students last time was, how does the velocity of the center of mass behave for a system of two objects that collide with one another, assuming their momentum is conserved, assuming they collide in such a way that their momentum is conserved? So we went over how to calculate the position of center of mass. Now we're working with velocity of the center of mass. Let's get a new sheet of paper out here. and get right to it. So two objects, let's say they slide on a frictionless table and they collide with one another. So here's m1 moving at velocity v1, and here's m2 moving at velocity v2. It can be moving towards m1 or it can just be moving away while slower. It doesn't really matter. I'll just say moving away at a slower rate. So that's before. And then after they collide, m2, whatever velocity it moves at, v1 initial and v2 initial, I should say, and then m2 moves at v2 final after the collision, and m1, maybe it bounces back and starts moving to the left, maybe it doesn't, maybe it just continues moving forward but slower. I'll say that it continues moving forward but slower, just so that we don't have to keep on flipping signs around. So that's going to be the after collision scenario. And I asked you to try and figure out how to find the velocity of the center of mass, both before and after the collision. So, if you get position of the center of mass and write it as a function of time, here's how that would work. Position of the center of mass, as you remember from the equation, is just going to be m1 times, I guess there's going to be some sort of distance between them. Let's go ahead and call this, x equals 0. Let's call that your 0 position. And let's call this starting distance d. Let's call this distance over here d, the starting distance between the two objects. Actually, I guess with the way I've drawn it, x equals 0 would actually have to be over here. Yeah, scratch that out and scratch that out. X equals 0 is going to be on this dotted line. So that's going to be the starting position for m1. For m2, I guess, how do I want to do this? Like, I know the conclusion in my head, but I guess I should have thought more and prepared more ahead of time for how I want to go about this. The position of the center of mass for the two objects is going to be m1 times x1, so yeah, we'll call this x1, plus m2 times x2. x2 being, I guess in this case it would be d, over m1 plus m2. Okay. Well, for velocity, if these things are moving at constant velocities, which they are both before and after, if these are constant velocities, then what I can do is I can say that change in the position of center of mass over change in time equals velocity of the center of mass. If they're moving at constant velocity, then this will work. This is the definition of average velocity, but if the velocity is constant, then it is the average. So that's going to be the velocity of the center of mass. And to get delta x center of mass, I guess I would have to do like 2 moments in time. So let's do x center of mass, we're still looking at strictly the before scenario here. So x center of mass final minus x center of mass initial over t final minus t initial equals m1 x1 final plus m2 x2 final minus, I'll put this in a group of parentheses, minus m1 x1 initial plus m2 x2 initial all over, of course, the t final minus t initial, but also over m1 plus m2. Okay. So m1 x1 final minus m1 x1 initial over t final minus t initial. Let's do that first. So let's factor out the m1 plus m2 in the bottom. Let's factor that out and shove it aside for a second. So I'll have 1 over m1 plus m2 times, I'm going to separate this. I'm going to group the m1 terms separately from the m2 terms. So I'm going to do m1 times x1 final minus x1 initial over t final minus t initial. And then it's going to be plus m2 times x2 final minus x2 initial. All over t final minus t initial. Well, again, this is all happening strictly in the before scenario, so imagine I'm just taking t initial is, at 0 seconds, and t final is like at, I don't know, 1 second before they've even reached each other, before any collision has happened. So m1 may have moved by, say, only this much, and m2 will have moved, I guess it would be a bit slower, and will have moved maybe by that much. That's basically what I'm trying to describe. So x1 initial would be over here, and x1 final would be here. x2 initial, I guess, would be here, and x2 final would be here, just the way I'm defining my x's. You could also do it from here to here. Should be the same difference either way. But yeah, x1 final minus x1 initial, that's just delta x1 over delta t, and x2 final minus x2 initial, that's delta x2. So m1 delta x1 over delta t, that's m1 v1. That's m1 v1, specifically here v1 initial, over m1 plus m2, plus this is just going to be x2 final minus x2 initial over t final minus t initial, that's v2. So that's going to be m2 v2, and then over the m1 plus m2. v2 initial should be. So that is the velocity of the center of mass in the before scenario, That's velocity of the center of mass before collision. Or you could just say it's a general formula for the velocity of the center of mass of two objects that are moving at constant velocities. So you could just write this as a more general equation for objects moving at constant velocity. m1 v1 plus m2 v2 over m1 plus m2, or if you had three objects, you would do a plus m3 v3, and then you'd have a plus m3 in the bottom, and so on, for however many objects you have. So this is a general equation for objects moving at constant velocities, how to find the velocity of their center of mass. Now, for the velocity of the center of mass after, then we could follow the same pattern. Instead of having to redo all our work here for the after scenario, we can just copy our previous work. This is going to be m1 v1 final will be the constant velocity in the after scenario, plus m2 v2 final will be the constant velocity of object 2 in the after scenario, over m1 plus m2. Now, how does the velocity of the center of mass before compare to the velocity of the center of mass after? Well, their denominators are the same, so any difference between them would have to be a difference between their numerators. And what about their numerators? If momentum is conserved here, what are these numerators? m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. So the conclusion, and this is the part that you want to take away if you're a Physics 1 student, you don't have to worry about this entire process, although, as you can see, it can be reasoned through with algebra, especially if you stuck around during the previous stream and learned the algebra-based approach to finding center of mass. But if you didn't bother with learning that because you're busy focusing on other stuff, then at the very least, the conclusion that you want to remember is this. In a collision, as long as momentum, I was about to say moment of inertia, as long as momentum is conserved, the velocity of the system's center of mass, in this case it was a system of two objects, but it could be more, the velocity of the system's center of mass does not change. It's the same velocity before and after the collision. And yes, if you wanted to take this reasoning to the next level, you could also define the acceleration of the center of mass. You will probably reach the conclusion. This is purely for your own interest. We're not going to use this for anything, but if you wanted to, you could find acceleration of center of mass, let's say for two objects. You should be able to reach the conclusion that m1a1 plus m2a2 over m1 plus m2 is also the acceleration of the center of mass for two objects that both have constant accelerations. So have fun with that if you really want to, but it's not really the most important thing for our course, whether you're in Physics 1 or Physics C. might come into play on some very rare occasion for Physics C, but I would not be placing bets on that. I would not be placing my bets on that. There are far more important things for you to be studying before trying to figure something like this out. Okay, now that we are done with that, it's finally time to start the actual lesson almost an hour into the stream. I mean, it's one of the big chapters. I did say that ahead of time. So let me see, where do I even want to start? So I guess we could, let me see what's on my list here. I didn't really decide on the order in which I wanted to present all these ideas today. I probably should have sat down and thought about that for a while, but didn't have the chance. Let's see, where do we want to start? I think I want to start more with moment of inertia stuff and then bring up the center of mass intuition, since some of those are going to be connected to each other. It's not going to make much sense to explain it without having a good grasp of moment of inertia first. That's the thing. They're so tangled that I don't know which one to start with, because I can see it either way. Actually, let's start with center of mass first. So, some interesting things that center of mass can do for you. Some of the things that center of mass can do. So, one thing that center of mass can help you determine is the stability of an object. Stability of objects. This is kind of a torque thing. You might know just from life experience that if you had a box, a rectangular box, you could set it on the floor in a number of different ways. One way you could set it on the floor is like this. Another way you could set that same box on the floor is like this. And in which orientation is the object less likely to tip over? Most people would say this, and you would be right. In this scenario, you're far less likely to tip over. Why? Well, it's because of how high the center of mass is in that first scenario. The center of mass, or more particularly the center of gravity, is where the force of gravity acts. So if the object is going to be tipped over, if I briefly touch this thing, if I poke it, if I disturb it in some way and I apply some force here, I could get it into an orientation where it ends up looking like this. And if I get it into that orientation and its center of mass is really high, then what's going to happen is, even if this force that initially started tipping it over, even if this force that nudged it disappears, the force of gravity could create a net torque on this thing that just continues carrying it down, allowing it to fall over. So the point where that happens is going to be, well, this would be the pivot point by necessity. When objects are in static equilibrium, we have the freedom to choose whatever pivot point we want. But when the object is not in static equilibrium, when there is a net torque, when it is rotationally accelerating, then the pivot is already set in stone for us. We don't really have a choice. This is the point around which the turning is happening for an object that tips over. It's going to tip over about the point of contact that is still touching whatever surface you have. In this case, we'll say the ground or a table or whatever. So if your center of mass is past this point, well, then the net torque is going to carry you past that point. So if I draw my r vector, my pivotal displacement, it's going to be this way. I can see from this that I'm already to the right of this pivot point, and I can see that whatever torque this force of gravity exerts, it's going to be in the counterclockwise direction, and counterclockwise is the direction of tipping over. Meanwhile, if I draw this again, where it has been tipped over, but not by too much, not as severely tipped over as the scenario above. Let's say it got tipped over like this, and its center of mass is here now. You've got your pivot point here. Force of gravity this time is on the other side of the pivot. So the force of gravity in this case is going to pull in a counterclockwise direction. Counterclockwise is just the box tipping back over to this side and becoming stable again. So the tipping point, pun intended, between these two scenarios is when the center of gravity is directly above the potential pivots being here, or if it was tipped over in the other direction, over here. So the harder it is to get the center of gravity over one of these 2 points, the more stable the object will be. And what makes it harder to get over these 2 points? Well, for one, the distance between the points. The farther apart the points are, the farther you have to go. The farther the initial nudge has to tip the object over in order for the center of gravity to actually travel the necessary distance to get past one of these potential pivot points. So having an object resting on its wider side allows that to happen, makes it harder for this center of gravity to travel far enough. Over here, it has to travel at least this far in order to tip over, whereas over here, it only has to travel that far. So increasing the distance required for the center of gravity to travel in order to get above one of these potential pivot points, one of these support points. Increasing that distance helps increase the stability of the object, decreasing the risk of it just falling over on its own after a brief nudge. The other reason that you want the center of gravity to be lower is because lowering the center of gravity decreases this. I drew it earlier, a little too early, but it decreases this pivotal displacement. The greater the pivotal displacement, the greater the torque. So if you're trying to, let me draw a tipped over, a nudged over version of this box over here for comparison. Wait, I drew it wrong. It's supposed to be tilted. It's supposed to be like this, and yeah, I messed up this drawing, but okay. Forget about the left side of this, just focus on the right side. Here's your force of gravity, and then let me get my other pen. If I take this r times the sine of this angle, then r sine theta is going to be... Wait a minute. Did I even do this right? Well, yeah, I guess I did. So r sine theta for this versus r sine theta for this. Wait a minute. No, that's not right. What am I doing wrong? I mean, with the way I've drawn it, it has a bigger r this way than this way. And I guess the sine theta part of it doesn't matter because the angle is going to be changing anyway as the object tips over one way or the other. Okay, so let's just focus on the magnitude of r then. So yeah, the magnitude of r is going to be greater in this orientation versus this orientation, right? It's going to be, if you imagine it's going to be some fraction of the distance between the support point and the center of gravity. Well, I guess that diagonal would actually be the same length. Hold on. No. What am I doing wrong here? Let me think. So you've got displacement this way, you've got this, the component of it that is perpendicular to the force would be this. Over here, the component perpendicular to the force would be this distance. It's the same either way. Assuming it's the same box with the same dimensions and everything. I guess then what we would have to do is compare different boxes. So compare a short box like this with a taller box that has the same width. Okay, here we go. And then for the shorter box, the lever arm is going to be, well, shorter than it is for the longer box, and a greater R leads to a greater torque, which makes it easier for the object to tip over due to the force of gravity. Torque gravity is going to be R times force gravity times sine of theta. Assuming these two boxes have the same mass, but this one is just taller than this one would be less stable. This one would tip over and fall more easily if it gets a sudden slight nudge. It has a higher risk of falling over just because it's easier to generate a lot of torque due to gravity. And I think that is everything we need to say about the stability of objects. So, just something you want to remember. You might get asked a quick, multiple choice question about it, if they ask about it at all, because I haven't noticed them being in the habit of asking that much about stability. Although, I guess now that I'm talking about it, I guess I should also talk about equilibrium in light of this. So there's actually two different kinds of equilibrium that an object can be in. There's stable equilibrium and unstable equilibrium. And the difference between the two is whether or not the object is able to return to its equilibrium state if it gets nudged out of it. So I guess continuing with this situation, if I have, let's compare a tall box to something like a pencil. If you are perfect, if you're absolutely perfect, you can get a pencil to stand on its tip. You can get this pencil to rest in equilibrium, but this is what we would call an unstable equilibrium. This is what we would call an unstable equilibrium, because here there's only one support point. Here there's only one support point, which is, of course, at the tip. There's only one support point. So if the center of gravity of this pencil is shifted even by an atom away from this line, if it shifts even one atom's width away from this line to the left or to the right, if you sneeze at it, it will tip over. There's no ifs, ands, or buts about it. That is what we would call an unstable equilibrium. Whereas if you have the tall box and you tip it over, as long as you don't tip it over too far, there's two potential support points here. And the center of gravity, as long as you don't move it more than this far to the right or this far to the left, then its torque due to gravity will actually bring it back to equilibrium, as I was saying with this scenario back here, right? If your center of gravity is still between your two support points, the net torque will, or at least the torque due to gravity, I don't want to say net torque because I don't know what other forces could be acting on this, but assuming no other forces are involved, assuming only gravity is there, the net torque due to gravity would actually help to reestablish the equilibrium, would try to bring it back to the position where it was just in equilibrium. So this is what we would call a stable equilibrium, and of course, stable here is a relative concept. Some equilibria are more stable than others. Yes, I said equilibria. The plural of equilibrium is equilibria. Very much like how we mentioned a few episodes ago that the plural of momentum is momenta. And the plural of maximum is maxima, and so on and so forth. So stable equilibria will vary. Some of them are going to be more stable than others, as we established back here. Okay, that is everything there is to say about stability. Probably not the most important topic. In fact, you might go through the whole entire AP exam and not get asked about it at all. It's actually quite likely, because I don't think I've ever seen a question about stability on the AP exam, but I know some AP physics teachers care about discussing this topic, and I mean, it's pretty easy to understand, so there you go. So that's one thing that center of mass helps us with. It helps us predict the stability of an object. Let me see what else I have on my list. So stability, I can check off. Actually, if we want to talk about stability, there's something that you might want to look into. Maybe I'll do a video on it, but you can try looking it up yourself. There's something called the book stacking problem. The book stacking problem. Which is rather interesting because it proves that you can stack books infinitely far away from the edge of a table and not have them tip over. So your first book would be like over here, and then the next book would be stacked on top of it like this, and eventually the stack can actually reach really, really far past the table. But it is a bit of a headache to, well, maybe more than a bit. It is quite a headache to go through, especially when you're looking at it for the first time. So brace yourself if you do decide to look into it. I'm not promising a video on it, but maybe I just will. Not promising anything yet, though. Just letting you know that it exists. And maybe looking at it will help you at least kind of conceptually understand that there's a lot you can do with manipulating centers of mass. Anyway, let me look around here and see what else I can say about center of mass. That I will leave for later. Okay, how about this one? So the center of mass of an object, here's another thing that we need to know about center of mass. Actually, I should probably repeat some of the stuff I said in the previous stream for the Physics 1 students who left for that part. We'll go over it. So, the center of mass of an object's center of mass, need not be on the object itself. Need not be on the object itself. For example, if I have two objects and I'm trying to find their mutual center of mass, let's say one object of mass m and another object of mass 2m, their center of mass is going to be closer to the 2m than the m. It's going to be closer to where more of the mass is, typically. It's going to be about 2/3 of the way, well, actually exactly 2/3 of the way with these numbers. And as you can see immediately, the center of mass is not on either of the two objects. I suppose if I connected the objects by a rod, then it would be on the rod connecting the objects in that case. But even if I had like a single continuous object, the classic example is the boomerang. If I have a boomerang, its center of mass is actually going to be somewhere out here. Its center of mass is actually going to be somewhere out here, just a point that you can't even physically touch. I mean, I guess you can touch the air at that point, but that's not really what I mean by being able to physically touch the center of mass. I'm talking about there's nothing solid there that you can touch. So yeah, an object's center of mass doesn't need to be on the object itself. But regardless of whether it's on the object or not, the center of mass does behave in a way that you can see pretty clearly if you manage to mark it. So I guess in the case of something like a boomerang, what you would have to do in order to mark the center of mass is maybe tie a string over here. Tie a string on here and then, I don't know, attach something light like a sticker or something where the center of mass is supposed to be. And then if you throw that thing at an angle, I already drew this in the previous stream for the Physics C students, but it bears repeating. If you throw that thing at an angle, then even though the boomerang is going to rotate wildly, its center of mass is going to follow the path of a projectile. Its center of mass is going to move like this, exactly as you would expect a projectile to move from way back in chapter, what was it, 2? But the boomerang itself, of course, is going to be just kind of moving somewhat chaotically. Like at this point, it'll probably be facing with its tip upward. Maybe at this point, it'll be facing with its tip having slightly rotated over here. Maybe it's facing like this. Over here, maybe it's like this. I'm not drawing it really well. Maybe over here, it'll be kind of facing straight down, and then over here starting to tip like that. So basically it's rotating. I guess I've drawn it rotating clockwise. At every step. So yeah, that's another property of the center of mass that you're going to want to remember. Actually, going back to the topic of stability real quick. So if you can get a support point directly under, if you can get at least 1 point, preferably you would want, more than 1 point. Preferably you would want like 2 or more support points with the center of mass somewhere between them. But at the bare minimum, if you can find one support point, 1 point that you can hold an object directly below its center of mass, then that is a point where, at least for a time, until it gets nudged hard enough, that is a point where the object can stay balanced. That is a point where the object can stay balanced. So I've got something like a boomerang, this toy that was really popular back when I was a kid. Like every mom in the neighborhood had a ceramic or porcelain version of this toy decorating some part of their house somewhere. Let me show you the actual pictures of it. This thing over here, the balancing bird toy. So it's kind of shaped like a boomerang. The wings usually they have like some sort of metal weights in them or something like that. The wings they have a heavier material in them that shifts the center of mass to somewhere further in front of the bird's head. And that's what allows the bird to just kind of balance at its beak. And you can, of course, hold it with your finger, as you can see in some of these images. None of these are drawings, these are all photos. But yeah, this is a thing that you can do. If you can find an object's center of mass, then you should be able to balance the object with one finger under that center of mass, provided that the center of mass is somewhere you can physically touch. So if this was a real boomerang, this wouldn't work, but with the bird version, they've made it so that the center of mass is at a point you can physically touch, at the beak. So yeah, there you go. If you want to buy one of these toys, you actually have to order them online nowadays, because I couldn't find a single place in my area where I could just go and pick one up. All of them require you to just order them online, and I'm not paying whatever amount it is in shipping. You'd pay more in shipping than you would for the actual toy. That's not worth it. But there you go. So, if you can find the center of mass of an object or a group of objects, then you can find the point where you can hold it, where you can balance it. If you have something like, well, I mean, with a ruler it's easy. You just go under the 6-inch mark, maybe a little bit off because there is this gap over here that subtracts a bit of mass. Not too significant, but also I'm using the width of my finger to create more support points, so it's not really on the tip of my finger. Maybe it would be harder if I tried to balance it like on the edge of a fingernail. Yep, I can feel it slipping. Hold on. Yeah. Trying to balance it on the tip of a fingernail is a little bit harder, but still doable. And I guess I'm kind of cheating because I can't feel it touching my skin under the nail. Okay, maybe. Yeah, I almost had it there. It's a little bit harder, but yeah, if you want to play around with this idea some more, boy, do I have a demonstration for you. Let me go get it. Ladies and gentlemen, I present to you one of the most overpriced physics demonstrations of 2025. A carton of eggs. These things jumped up like 300% in price practically overnight. Funny how the election didn't change that. But yeah, you can play around with something like a carton of eggs, assuming that your eggs are identical, which I guess they're not, because some of them are bigger and some are smaller. But if you play around with this, you can freely shift around the center of mass of this thing. So right now I have it all symmetrical, so if I were to use my finger to balance it, I would just do it over here. I guess you can't see that really well, but my finger would be down here at this point, but it wouldn't balance so well if I started shifting the center of mass down. Now you can kind of see it. Now you can see it just kind of tipping over. You can play around with this and move the eggs around, and this will get you like more of a physical sense for center of mass. So this is definitely an experiment that you can do at home. Maybe do it over a table in case, your finger slips, you don't want to break the eggs, or better yet, hard boil the eggs before you start playing around with them. But yeah, this will also help with intuition. It'll help you kind of quickly look at objects and see, okay, more of the mass is on this side than this side. The center of mass is probably closer to here. Maybe I should grab it from under this point instead of the center to get it to balance. And this is probably, again, a bit of cheating because I'm using kind of the width of my fingertip to create more support points, so I'm not being pinpoint precise with my finger placement. Not that the shape of this carton would really allow me to, but yeah, easy home experiment that you can do, even though in 2025 it is rather overpriced. All thanks to bird flu. We can blame it on Joe Biden, though, right? That's what everybody's saying. Half the country is blaming it on Joe Biden, half is blaming it on Trump, and the real ones know that it's because there's a mini epidemic. Well, maybe not a mini epidemic, but there's an onset of avian flu going around right now. Anyway, I'm going to go ahead and put my eggs back in my fridge so that I don't lose these. After all, they're quite overpriced. I'll be back in a minute. All right, I am back. Was there anything else I wanted to say about center of mass? Let me check my list. Because usually I teach each of these concepts in separate lessons. This is my first time trying to get it all in one lesson, so kind of need a list to make sure that I'm covering everything. Did that. I talked about that. We did that. So I guess a little bit more on that egg stuff, just talking about guessing center of mass. That's something that you would want to get good at, and the egg carton demonstration will help with that. But generally, just if you're looking at some weirdly shaped object, some strategies could be like, finding a sort of halfway point. It doesn't even have to be a perfect halfway point, just for making quick, educated guesses. You could just draw a dividing line where you think, okay, about half of this object's mass is on this side of the line and half of it is on that side. I guess with the line I've drawn over here, that doesn't seem to be the case because the size of this blob is smaller than the size of this blob. So unless the density is higher on the right than it is on the left, this is probably not the line along which the center of mass would be. I would probably want a line that's closer to here, maybe. And now, yeah, this shaded region looks to have about the same amount of mass in it as the unshaded region, and then do it again along another line. They don't even have to be an X line and a Y line. You can draw actually any number of lines that you think evenly divide the mass of the object, and wherever those lines intersect, wherever those lines meet, that's where your center of mass of the object is going to be. Again, you're not going to be able to do this precisely. You're only human after all. But the point is, it gives you the opportunity to make an educated guess. It allows you to make an educated guess, and it also allows you to check your work. Maybe if I have an object that's less curvy, let's say I have, for example, I don't know, a rectangular shard of glass. And if you happen to have one lying around, or, well, maybe not glass, but maybe if you have like a rectangular piece of wood or something like that, you could try and play around with this. Did I say rectangular? Triangular. A triangular piece of glass, wood, whatever, like this. You can see that it's a bit more lopsided. It seems that more of its mass is on the bottom than the top. So if you want to still draw a line just halfway along the height, that's fine. And then that gets you to establish, okay, there's less above the line and more below the line, then my center of mass needs to be somewhere below this dotted line. And then if I draw another dotted line like halfway along the base of this triangle, I can see there's less to the left than there is to the right. So it looks like somewhere down and to the right is where my center of mass will be. So if I had to make an educated guess, maybe I'd say somewhere like here. So yeah, just draw some dividing lines, maybe cut it into 4 sections like this and see which section has more mass in it, and that's probably where you want to pinpoint your guess for the location of the center of mass. Sometimes a guess is all you need. Sometimes you'll get like a multiple choice question that just shows you, for example, 4 pictures of this triangle, or 5, A, B, C, D, and E, and each one of them is going to have the center of mass marked at a different point, and you have to pick the one that is most correct. So get good at guessing, get good at estimating the position of center of mass for some lopsided shapes. And I think that is all I have to say about center of mass for now. We'll bring it up again one more time when discussing moment of inertia, even though I actually did bring it up last time. The center of mass of an object is where the moment of inertia for an object is lowest, and moment of inertia, as we will repeat soon, is an object's resistance to being rotated. So the center of mass is where you want to go if you want to have the easiest time twirling something. The center of mass is where you want to go, because doing it from somewhere further from the center of mass, like from the edge, you're going to have a harder time making it twirl and twist and rotate, which could be a good thing or a bad thing, depending on whether you want it to twirl and twist. Okay, so moment of inertia, finally. Moment of inertia. We talked about it a little bit last time, and I'm going to repeat some things. So it's an object's resistance to being rotationally accelerated, and as a result, it obeys a law that's very similar to Newton's second law. Newton's second law says net force equals mass times acceleration. The more mass an object has, the less it will accelerate for a given amount of force, or in other words, the more force it requires to achieve a certain acceleration. Well, for rotating objects, the net torque required to rotate an object increases the more moment of inertia it has. The more moment of inertia an object has, the less angular acceleration you get for your torque. You're going to need a lot of torque if you want a lot of angular acceleration for an object with high moment of inertia. Objects with high moment of inertia do not turn so easily, do not rotate so easily. So, like I said last time, if you just remember, a lot of the rotational analogs of quantities that you learned in the past, if you remember your equations from the past, a lot of them are just a quick take the equation you already know, replace the variables in it with the rotational versions of those variables, and you're good to go. One thing I didn't talk about last time is the units of moment of inertia. So let's talk about how to find moment of inertia. I did say for a point mass, an object that's being treated as if all of its mass exists at a single point, moment of inertia for a point mass is equal to the total mass at that point times the square of the distance between that object and its axis of rotation. So if I have an object over here and I have an axis of rotation like this, and it's going around that axis of rotation, it's going around like that, then r would be this distance over here. It's specifically the perpendicular distance between the object and its axis of rotation. It's specifically the perpendicular distance. And this version of the or rather this equation involving moment of inertia, I should say, tells us what units moment of inertia should have. The units for moment of inertia are going to be mass units times distance or position units squared. So it's going to be kilograms times meters squared is the standard unit. The standard unit for moment of inertia is a kilogram meter squared. Let me see where I want to go from here. Yeah, I really should have taken the time to kind of just structure and order these topics a little bit ahead of time. Would have made for a smoother experience, but it's okay. We will reach the same destination in the end anyway. Let me think. So we've talked about this and this. What would make the most sense to go over next? So I did talk about last time how this R factor is an important factor. I did my little umbrella demonstration, and we saw that mass isn't the only thing that's necessary to resist rotation. In fact, this usually turns out being the more important factor, this distance factor, and you can probably see that from the equation because unlike the mass, the distance gets squared. So it should have a greater effect, all other things being equal. So if I go ahead and look at something like a meter stick, we said last time that the reason that greater length leads to greater resistance to rotation, what we said was if I was just looking at this thing tipping over, going around an axis that goes through its end like that, what we said is that if I chop this into little pieces, and you have some parts of it that are further away from this axis of rotation than other parts, then what's going to happen if this thing were to tip over is that this piece only has to travel this far, this piece over here has to travel a lot farther in the same amount of time, and then the pieces that are furthest out have to travel the farthest distances in that same amount of time. So increasing distance from the axis of rotation from this we can see requires more force, or rather requires more torque resulting from that force. And we talked about what happens if you try and force the situation, if you try to make these lower parts reach their destination as quickly as possible without waiting for the rest of the object to catch up. We talked about how you can get bending, or even worse yet, you can get breaking of the further away parts of the object. So no need to rehash that, just understanding the intuition. The farther away the mass is from the axis of rotation, the harder it is to rotate. So with that understanding, let's go ahead and compare a bunch of different objects that are not point masses. let's compare a bunch of different objects that are not point masses. For these, you actually need calculus to derive the formulas, and I will show you how to do that for the Physics C students. We will do that on the revisit. All the calculus stuff will be after we're done with doing everything algebra-based, as I've been saying over and over again. It bears repeating in case some new people are here and don't know that. But for now, I'm just going to give you a bunch of formulas. So we have a couple of different shapes that occur pretty frequently that will be of interest to us. One is the rod. And actually we have two different moment of inertia formulas for it, although technically you only need one of them. So one is a rod through an axis through its end versus another one is a rod or a stick being rotated through an axis through its center. For this one, moment of inertia for a rod through its end is going to be 1/3 of its total mass times its total length squared. Again, these formulas come from calculus, but I will give you kind of a method to approximate this that you might find satisfying if you're just working algebra-based. Not something that you need, but I think it's something that can help you at least find this somewhat convincing. We'll go over that later. Here it's a rod through its central axis, or rather through its center, through an axis perpendicular to it and through its center. This, do you expect it to be greater or smaller than 1/3 ml squared? Let's see if you've been paying attention. Here, the axis is really far away from this end of the rod, whereas over here, the axis of rotation is a lot closer to the two ends. Now, perhaps because there are two ends instead of just one end, perhaps that makes up for this? Nope. Nice try, but no. The closer you are to the object's center of mass, the lower the moment of inertia. For a rod being rotated through its center, after you do the calculus, it turns out that the moment of inertia is going to be 1/12 of its total mass times its total length squared. And you're going to notice there's going to be mass times something, length, radius, some sort of distance unit squared every time, and that should make sense because our units need to be kilogram meters squared in the end anyway. Or grams, centimeters squared, or whatever alternative units you want to use for mass and length, but kilograms and meters are the standard. Next, let's have a look at a solid sphere. So, specifically, it's a solid sphere rotated through an axis going through its center. So this is going to be I, sphere, solid. And the moment of inertia for a solid sphere. By the way, in case I didn't mention this, you do not need to have any of these formulas memorized, although I would recommend memorizing the rod through its end, and also perhaps the rod through its center, although you don't necessarily need it. I'll show you later what you can do instead with just this. And I would also recommend knowing the disk or cylinder, which we will show later. So for a solid sphere, it's going to be 2/5 the total mass of the sphere times its radius squared. For a hollow sphere, which I guess is going to be the same picture really, because the difference between them is whether or not there's anything on the inside, and I'm not sure how to draw the inside and the outside at the same time, but sphere hollow, also known as a spherical shell, if you will, is going to be higher or lower, do you imagine, if they have the same mass, but the mass is arranged differently. In the solid sphere, the mass is taking up all of this volume. It's spread out through all of this volume, whereas in the hollow sphere, if they have the same mass and the same radius, the hollow sphere takes all of that mass and puts it all on the outside, none of it on the inside. You would expect, if you started with this and you started removing mass from the inside and putting it onto the outer surface, you would expect that to increase the moment of inertia because you're moving some mass away from the axis. You're moving it further out onto the surface. So for a hollow sphere, it does make sense once you see that it's 2/3 the mass of the hollow sphere times its radius squared. A hollow object, a hollow version of the object will always have a higher moment of inertia than the solid version of that same object for the same axis of rotation, that axis of rotation being through its center, at least. For other axes of rotation, I suppose there might be a change. Actually, I haven't really thought about that, so I'm not going to comment on that until I've had some time to think about it. But at the very least, if your axis of rotation is through the center, then the hollow version will always rotate slower than the solid version, will always resist rotation more under the same amount of torque. Okay, so that's the sphere, and then we have the cylinder or disk. This is one of the ones that you should probably remember, and fortunately, it's very easy to remember. So for a cylinder or disk, specifically with an axis of rotation through its center, through the center of its circular base. So this is I. Cylinder or disk is 1/2 of its total mass times its radius squared. And then the hollow version of a cylinder or disk is a cylindrical shell or a ring, a hoop. So this is I ring or hoop, I'm just going to call it a hoop, is equal to, actually you can probably figure this one out. If you chop this hoop up into a bunch of pieces and you get the moment of inertia of each individual piece, if you chop it into small pieces that can each be considered point masses, then each piece of this hoop is going to be some little m times the same distance squared, right? All the pieces, whether I pick this piece over here, or this piece over here, or this piece over here, whatever their masses are, their distances, their r squared is going to be the same for each and every one. So m1 times r squared plus m2 times the same r squared plus m3 plus m4 plus add up all those little m's, all times the r squared, that's just going to be the total mass, big M, times r squared. No fraction in front. So for a hoop or ring, And it can also be, it could also be a hollow cylinder, and that won't matter. If you have some height to this, if I were, let me draw another one. If I were to draw a cylindrical shell, I'm not sure how to show that this is a shell and not a solid cylinder. How would I go about doing that? I'm not sure. I don't have the art skills for it, but this is a cylindrical shell, so it's like this, right? It's like a toilet paper or napkin roll is what I'm describing. In that case, it's still just mr squared. The height doesn't make a difference here, because what you would be doing is, instead of chopping it into little points along a hoop, you'd be chopping it into little strips along the cylinder, and each strip is going to be, well, the same r squared from the axis, so you just add up the masses of each of those strips times r squared, and you get the same result. So cylinder shell is also just mr squared, the total mass of the shell, times its radius squared, for an axis of rotation through its center. Very important to emphasize that. I mentioned it last time, and I will mention it again here. An object does not have a single moment of inertia. Every object has multiple moments of inertia, infinitely many, one for each conceivable axis of rotation you can think of. So it's very important when somebody tells you, what's the moment of inertia of a solid sphere? You say, through which axis? You call them out on it. If they don't specify the axis, you tell them how the tutor sent you. And I don't know where I was going with that. I was trying to imitate the outros of Josh from the Don't Be Dumb videos on YouTube. I'll have to link you guys to some of those. They're pretty funny and educational. Anyway, let me figure out where I want to go next before I get too lost in tangents. So I wanted to do what? Well, I want to at least give you a method to try and approximate moment of inertia for something like a rod through its end. I want to give you a technique for you algebra-based students to at least approximate it and convince yourselves that it makes sense. It'll probably be a very time-consuming process if you want it to be, you know, even remotely precise, but I'll get you started on it at the very least. So if you have more than a point mass, then what you can do is you can get moment of inertia as the sum of a bunch of masses times their distances squared from an axis of rotation. Basically, you can chop an object up into little pieces, m1 r1 squared, whatever the distance of point 1 is, squared times its mass, plus mass of point 2 times distance of point 2 squared from the axis, plus m3 r3 squared, and so on and so forth for however many point masses you can chop your object into. Now, for a continuous mass distribution like a rod, there's an infinite number of points, so you're actually going to need calculus to get anything precise. But if you want to at least get an approximation, you can do that. You can do I rod approximation is equal to, let's take a rod, actually, to approximate with, and I don't want to chop it up into too many pieces or else we'll be here all day, but let's say we have a rod rotated through an axis through its end, and let's chop it into, I will do 8 pieces. I think 8 is manageable. And let's see how close we get to 1/3. So I'm going to chop it into 8 pieces, and this is a uniform rod, by the way. All of these are uniform objects. So the mass is going to be distributed evenly. So if I chop it into 8 pieces of equal length, then I should have 8 pieces of equal mass as well. We'll say the total mass of this rod is m, and the total length is L. And so each individual piece is going to have a length of 1/8 L and a mass of 1/8 M. And let's see what we can do with that. So I'm going to actually use the center of mass of each piece and treat each piece as existing at its individual center of mass. So if this distance over here is 1/8 of L, then the center of mass of the first piece is actually going to be at 1/16 of L, and then the next piece is going to be at 1/8 more than that, so 3/16 of L, 5/16, 7, 9, 11, 13, 15/16. So that's what I'm going to do. And then each object is going to have 1/8 of the mass. So since the masses are all going to be the same, I'm going to go ahead and factor out the big M over 8. So the mass of each one is going to be big M over 8 times the distance of each one is going to be, for the first one, R1 squared is going to be 1/16 squared, plus the next one is going to be 3/16 squared, and I didn't write this correctly, I should put parentheses around that. 3/16 squared plus 5/16 squared, and so on. This shouldn't be too many inputs for a calculator. Plus 9/16 squared. Come to think of it, since the 16 is reoccurring, we can factor that out as well. And I guess that's what I will do for when I get to putting it in my calculator. And then plus 11/16 squared, and plus 13/16 squared, and plus 15/16 squared. And then close the greater parenthesis over there. Okay, so we've got 1 plus 9 plus 25 plus 49, 1 plus 9 plus 25 plus 49 plus 81 plus 121 plus 169 plus 225 is 680 over 16 squared is going to be 256. It's going to be 256, and then 256 times 8 is 2048. So I get M times, oh, and I forgot the L squared, didn't I? Yeah, it's 1/16 L all squared and 3/16 L all squared, and so on and so forth. So factor out the L squared as well. Almost forgot that. Glad I caught it. So it'll be ML squared over, we said 256 times 8, which is 2048, and then times the sums of the numerators would be 680. So if I do 680 over 2048, let's see what that simplifies to. That simplifies to 85 over 256, so we get 85 over 256 ml squared. And if I just go ahead and do division, 85 divided by 256 is 0.332. It is about 0.332 ml squared. That's almost a third. That's almost a third. And if you were to chop this up into even smaller pieces, say you chopped it up into, I don't know, 20 pieces, 30 pieces, 50 pieces, 100, you'd have a lot of writing to do. But you would also notice a trend. You could probably just set up like an Excel spreadsheet to automatically do the calculation for you to save yourself time. But yeah, if you chop it up into more and more pieces, the more and more you repeat this with more and more pieces, the closer and closer this will get to being exactly 1/3. You'll never actually get there because you would need an infinite number of pieces, and for that you need calculus. But without calculus, you can at least chop this into enough small pieces to convince yourself that this 1/3 must have some truth to it. So that is how to get an approximate moment of inertia for some sort of rigid, continuous object. Now for using this to find this. This is going to be the fun part. This is something that a lot of people would immediately think you need calculus for, but you actually don't. So I'm going to do it for a rod through its center first, but my big question is going to be, what is the moment of inertia for a uniform rod whose axis of rotation is at 2/3 of its length? Or 1/3 if you're coming from the other direction, I suppose. That is the question that I am trying to ask. Well, the trick is to split it up into 2 rods rotated through their ends. So I'm going to do this with the rod rotated about its center first, and I'm going to utilize this little bit of space over here to draw it. So a rod rotated through its center can really be thought of as 2 half rods. I don't know why my drawing is tilted like that, but we'll go with it. You can think of it as 2 half rods. So here's one half rod, and here's another half rod. And the moment of inertia of the full rod is just the sum of the moment of inertia of each half rod. You have to be very careful here and make sure you keep track of the masses and lengths, but you should be able to get this 1/12 ml squared if you're careful. If you can split an object into multiple other objects, all you have to do then is take the moment of inertia of each individual part and add them together. Whenever you have multiple things as part of some sort of total object or system of objects, you can just calculate the moment of inertia for each of those parts individually and add them. It's as simple as that. Moment of inertia for an object is simply the sum of the moments of inertia of each of its individual pieces. So this is 2 rods of mass m/2 and length l/2 rotated through their ends. I'll calculate the moment of inertia for one of these half rods and then just multiply by 2. and then we'll get to this actual problem that I want to do. So, moment of inertia for a rod through its end is 1/3 of its mass times its length squared. So the moment of inertia for this half rod is going to be 1/3 of its mass, which is m/2, times its length squared, which is L/2 squared. We're going to take all this and multiply it by 2. And let's see what we get. So the 2, I guess, will cancel with this 2 over here, so that saves us a little bit of writing. And then L/2, when I square it, I get L squared over 4. L squared over 4 times m and times 1/3, so the 1/3 and the 4 in the denominator, that's 1/12. And ml squared. There you go, we're done. It's as simple as that. So each half rod would have been 1/4 ml squared, and since we've got 2 of them, you get 1/2? No, 1/12. 1/3 times the 4 in the denominator, that would be a 12. My bad. So actually, each half rod would be 1/24. What was I thinking? Each half rod would have a moment of inertia 1/24 ml squared, and when you put them together, you get 1/12 ml squared. Now let's try and use the same strategy for a rod rotated through an axis that is 2/3 of the way along its length, or you could also say 1/3 of the way along its length from the other side. So this will be L/3. And this will be 2L/3. And of course, we assume the rod is uniform, so 2/3 of the length would contain 2/3 of the mass. Let's figure out what the moment of inertia of this thing would be. I'm just going to use, again, moment of inertia for a rod through its end. So I'm going to say it's going to be I total equals 1/3 of, let's see, the first one is going to be 2/3 m times the square of 2/3 L, plus the second one is going to be 1/3 of, the second piece is this 1/3 piece. It's going to be 1/3 m for its mass, and for its length squared, it's going to be 1/3 L and squared. Okay. We can factor out all these denominators. We've got a bunch of 3's. We've got a 3 and a 3 and a 3 squared. That's going to be 3 and 3 is 9, and 3 squared is another 9. 9 and 9 is 81. So we already know the denominator is going to be 1/81. I'll leave the numerator blank until we find out what goes there, but we've got 81. And we know that we're going to have an m. And we know we're going to get an L squared. So now for the numerators. We've got 1 times 2 times 2 squared is going to be 8. And then plus 1 times 1 times 1. So we've got 8/81 plus 1/81. Wait, is that right? 1. Yeah, we've got 8 there and 1 there. Yeah, 9/81 ml squared, which is going to be 1/9 ml squared. ml squared. Hopefully that is still readable. I know I had to kind of squish it in there in the end. I don't remember it being like this. I remember something a bit more complicated. Let me double check my work, because I feel like this might be wrong. So we've got 1/3 times 2/3 times 2/3 squared. So that's 1 times 2 times 4 is 8 over 81. And that's, yeah. Okay. Yeah, it's 1/9 ml squared. I feel like I was getting a different result with the examples that I usually give to my students, but maybe the example I gave them was 1/4 of the way through the rod, because I don't remember it simplifying so well. Well, if I catch a mistake here when I'm timestamping, trying to go through it and figure out where to put the timestamps in the stream, then I will post a pinned comment mentioning a correction, but I don't see anything wrong with it right now, so we'll just go ahead and say that it's probably right. But at the very least, whether it's right or wrong, what I want you to take away from this is just the strategy, the process. For rods, it's really, really easy. A rod through any axis of rotation, you can just split it into 2 rods through their ends. That's the important thing to take away from this. Not that they would even ask you this on the AP exam, I don't think, because, well, they could. They don't expect you to memorize these formulas. They don't expect you to memorize moment of inertia formulas for all these different shapes. But if they do end up asking you to use these, then they will give you the formula in the problem, or they will give you enough information where, like, part A or part B of the problem will be to complete whatever information they gave you in order to derive these formulas. And you won't be, like, deriving them from scratch. They'll probably just give you, I don't know, like, the net torque on an object and the angular acceleration that resulted from that, and then you work backwards from there to figure out what moment of inertia formula the object must have had. So yeah, they won't ask you to do anything like this if you're Physics 1. If you're Physics C, though, all bets are off. You can do calculus. They will ask you for shapes like these. They will ask you to take advantage of symmetry. They wouldn't ask you to do the hollow sphere, I don't think, because that one is a bit too mathematically challenging. I don't think they would ask you for that one. Most likely, they would ask you to do a rod or a disc or cylinder. Worst case scenario, they might ask you to do a solid sphere, but I don't think that's likely. But I'll show you how to do all of them eventually. Actually, I think I already have a video from a few months ago where I did the solid sphere. It was one of my traditional office hours videos that I had to stop doing because, my goodness, could you imagine if I was still doing them right now with how sporadic my schedule has been? I'm barely keeping up with these videos. Or streams, rather. I keep calling them videos or streams interchangeably, though there is a difference between the two, I suppose. Anyway, that's enough of me rambling. Let me figure out what we need to cover next. So, let me look at my list and see if there's anything. Ah, right. This is actually a good way to check my work. The next thing that we want to talk about is the parallel axis theorem. For the Physics C students, we will go over the calculus-based derivation whenever we get to the calculus part of the course. But for now, we will state this without proof. The parallel axis theorem. Here's what it says. If you know the moment of inertia for an object through its center of mass, and you try to calculate its moment of inertia through any other axis that is parallel to that axis through its center of mass, then I nu, moment of inertia with respect to the new axis, equals the moment of inertia through the center of mass plus the total mass of the object times d squared, where d is the distance between the axes. So we can demonstrate this really easily with the rod. We can demonstrate this really easily with the rod. So if I have a rod and I know its moment of inertia through its center of mass is, we got 1/12 ml squared, where L is its length, of course. And I want to get the moment of inertia for a rod through any other axis as long as it's parallel to this one. So for example, through its end. And I also want to add, because this will give me another way of confirming whether or not my previous result was correct, I also want to add 1/3 of the way along its length. So I want to do through this axis, and I want to do through, I guess I drew it over on this side, it doesn't matter which side I come from, but through that side, so that's going to be L/3. Okay, let me use another color to indicate the original axis. I'll use orange here. So the original, well, I guess original isn't the right term. The center of mass axis is going to be over here. So D is going to be the distance between the center of mass axis and the new axis that you're trying to find the moment of inertia for. And then over here, D would be this amount. So over here, D would just be L/2, right? It's a distance L/2 away from the center of mass, your new axis is. Over here, your blue axis would be, well, if this is the halfway point and this is the 1/3, then 1/2 minus 1/3 is what this would be, right? This would be L/2, and you're trying to subtract L/3 from L/2. L/2 minus L/3, that's 3L/6 minus 2L/6. 3/6 minus 2/6 is 1/6. So over here, D is equal to 1/6 of L, or L/6. So let's go ahead and use the parallel axis theorem to try and calculate what is going on here. Over here, moment of inertia through the end is going to be what it is through the center of mass, so 1/12 ml squared, plus m times, this is going to be L/2 squared. And it's always a plus, by the way. That's the thing to note. It doesn't matter which direction the new axis is from. The center of mass of an object is where the moment of inertia is going to be the lowest. So it can only increase from there. It can only ever increase from there. And we'll do a little bit of a pseudo calculation in a bit to help you kind of grasp that idea a little bit better. But for now, just take my word for it. since it's at its lowest at the center of mass, it can only increase from there. So this is always going to be a plus sign. Don't let anybody confuse you telling you that the direction of D has any sort of influence and should be substituted as a positive or a negative. I mean, even if you did do that, you're squaring it. So that's going to eliminate any negative signs anyway. So 1/12, not 1/2. I forgot the 1 in front of the 2. That's not good. 1/12 ml squared plus, this is going to be L squared over 4, so 1/4 ml squared. So that's going to be 1/12 plus 1/4 all times ml squared. 1/4 is 3/12. 1/12 plus 3/12 is 4/12, which is 1/3. Well, how about that? That's exactly what we said it would be through the end. Now let's try and do it for this. Can't wait to see how this turns out. So for this one, it's going to be I through, I guess, I called it 2L over 3, 1L over 3, whatever you want to call it, is equal to 1/12 ml squared plus m times L over 6 squared. So that's going to be, and I forgot the square this time. Each time I write this, I forget something. So that's going to be 1/12 plus, this is going to be 1/36. ml squared. 1/12 is the same as 3 over 36, so 3 over 36 plus 1 over 36 is 4 over 36, which does reduce to 1/9. Okay, now I'm a little more certain that what I got earlier was correct, but for some reason it's still bugging me. Because I remember doing something for one or more of my students where the fraction in front had like an odd number numerator and an even number denominator. Or maybe it was the other way around. So if it wasn't the 1/3, maybe it was like the 1/4 or something like that. Who knows? I'll figure it out later. But yeah, we're getting the same given formula in this case and the same result that we calculated earlier in this case. So that should give you some confidence that the parallel axis theorem is legit, even though we haven't proven it yet. So what can we do with this? Well, the parallel axis theorem can allow you to calculate the moment of inertia for something weird, like, I'll call it a carved cylinder. Let's say I have a cylinder over here with another cylinder carved out of it. So let's say it has this cylinder-shaped hole in it, but the rest of it is solid. So it's this sort of crescent-shaped cylinder thing, I guess. And we are calculating its moment of inertia through the axis shown here. How would we go about doing this, assuming that the mass of the full cylinder is m and its radius is big R? Again, that's the mass of the full cylinder is m. The mass of this thing is less than m because it's, well, missing the part that got carved out of it, that got hollowed out. So how would we go about doing something like this? Well, first off, if we know that this radius over here is big R, then that's the diameter of this thing. That's the diameter of this thing. So that means that the radius of this thing is big R over 2. Big R over 2. So what we want to do here is use the addition property of moment of inertia. It's already coming in handy, as you can see. Moment of inertia for an object is simply the sum of the moments of inertia of its parts. So if I think of the moment of inertia for a full cylinder, if I think of the moment of inertia for a full cylinder rotated through its central axis, if I think of the moment of inertia of this thing as being the sum of the moments of inertia of this thing plus its missing piece, which is this mini cylinder that got hollowed out. I guess I didn't draw it the right size, but R over 2 is what it should be. I should have drawn it a little bit bigger, but you get what I'm trying to say, I would hope. If we add these together to get this, then we can actually work backwards from that, and we can say that the moment of inertia of this thing minus the moment of inertia of this thing would have to be the moment of inertia of this thing. So what is the moment of inertia of this thing? Well, if it has half the radius, how much of the mass does it have? Assuming that it has uniform density, which is the natural assumption here, as we've been saying over and over again today, what fraction of the volume is this thing? Whatever the height of this thing is, this thing has that same height. So we don't actually have to worry about height here. Whatever fraction of the volume this thing is out of, well, I guess it would be out of this original cylinder, it's also going to be the area fraction of the base. So when you have R over 2, I didn't word that well, area fraction of the base, that doesn't mean much. You'll understand once we actually do the math here. So this thing has radius big R and mass m. This thing is going to have radius R and mass m. Actually, yeah, this thing is going to have radius R and mass m. So I'm going to say that its volume is going to be pi r squared. It's going to be pi r squared times h, and they're all going to have the same height h over here. The volume of this thing is going to be pi and then r over 2 squared times the same h. So if I take the ratio between these, the pi cancels out and the h cancels out. That's why I said the height doesn't matter. All that matters is what fraction of the area of the base will this thing take up compared to the original circle over here. Let's see, so that's going to be r squared over 4, so this is going to be 1/4 of the circular base area, which means it will be 1/4 of the volume since the heights are the same. So this is 1/4 of the volume, which means it contains 1/4 of the mass. So this thing has a mass of 1/4 m. I guess I'll call this ms for small. M small is 1/4 m large. And then, wait, what should I call these? let me come up with better names for these. I'm going to call this M full equals I'm just going to call this M full. I'm going to call this M small equals 1/4 of M full. And I'm going to call this M large equals, must be 3/4 of M full. And this lets me say that M large is also equal to 3M small. Or, if you prefer, I could go about it in the opposite way. I could say M small is equal to 1/3 of M large. If I want to express my final result in terms of the mass of this large piece, then I'm probably going to want to write M small like this. This is probably what we're going to prefer to use. Okay, moment of inertia for this thing will be given as 1/2 M full R squared. Moment of inertia of this thing, its axis of rotation is not through its center, so it's not 1/2 M small times R small squared. We have to use the parallel axis theorem to figure out what the moment of inertia is going to be for this cylinder on this new axis that is through its end. So let's go ahead and do that. Moment of inertia for a cylinder through its end, just a general cylinder through its end, is going to be I cylinder through its end is going to be, according to the parallel axis theorem, moment of inertia through its center of mass, which is 1/2 of its mass times its radius squared, plus its mass times d squared, where d here is going to be this distance, r/2. Wait, no. See, you got to be very, very careful here. Its distance is going to be r. This is a different m and r from all the m's and r's that we have over here. Yeah, you got to be very, very careful about this stuff, or else you'll easily get mixed up, as I almost did. Even the pros can get mixed up here if you don't slow down. So this is just some random cylinder that has nothing to do with these three, that's going to have a mass of m and a radius of r, and I want to calculate its moment of inertia through its end. So d for this thing is going to be r. It's one radius away from its center. So that's going to be 1/2 mr squared plus mr squared equals, well, mr squared is the same as 2/2 mr squared. So 2/2 plus 1/2. I'll write the steps. 1/2 mr squared plus m, replace the d with r squared. And then 1/2 mr squared plus mr squared is 3/2 mr squared. There we go. So any cylinder rotated through its end is going to have a moment of inertia of 3/2 its mass times its radius squared. So for this thing, it's going to be 3/2 m small times r small squared. 3/2. So I small equals 3/2 m small, which is, I'm going to write it as 1/3 m large, is 1/3 m large, times r small, which is going to be 1/2 r of the large cylinder squared. So that's going to be just r large over 2 squared. R large I'm just calling r. I suppose we could, put an L on there if we really want to. R, L. That works. So 3/2 and 1/3, at least the 3's cancel out. So there's that. And then we've got the 2 in the denominator gets squared into a 4. And then with the 2 over here, that gives us 1/8. So 1/8 m large r large squared. I small equals 1/8 m large r large squared. Okay. Now I want to express the moment of inertia of the full cylinder in terms of m large and r large as well. So for this, it's going to be, well, m full is going to be, if I take this equation over here and rewrite it, just multiply by 4/3 on both sides, I get m full equals 4/3 of m large. So that's what I'm going to substitute for m full. So moment of inertia for m full, I full is equal to 1/2 m full, so 1/2 of 4/3 m large, times r full squared, which is equal to r large squared. So no difference between these r's. This is equal to r large. And if I go ahead and simplify, that just gives me 2/3. 2/3, or no, not 2. Yeah, 2/3. 4 over 2 is 2, and 2/3. 2/3 m large r large squared. Okay, perfect. And now that we have this, we can say I guess large, I of the large piece equals I of the full piece minus I of the small piece. So I of the large piece is equal to 2/3 ml/rl squared minus 1/8. I forgot to box this. Minus 1/8 ml/rl squared. Oh boy. 2/3 minus 1/8. That's going to be 2 over 24, or no, what am I saying? 2 over 24. 16 over 24 minus 3 over 24. If you use 24 as a common denominator, 16 minus 3 over 24 is 13. 13 24ths. M large R large squared. So if you have something like this and they tell you its mass, you would use 13 24ths of its mass times its radius squared, and that would be its moment of inertia. Pretty tough, just because of the number of steps involved and because there are so many opportunities here for you to mix up your variables, because you have all these different masses and radii to keep track of, and you want to write your final answer probably in terms of the mass of the larger piece, although they might give you some leeway here. and have you write it in terms of the mass of the original cylinder instead, depending on how they word the question. Like if the question is worded, hey, we have this original cylinder, and then if they say, hey, we have this original cylinder of mass m and radius r, and then we carve out a hole in this cylinder, what is its moment of inertia now? In that case, you would actually want to write it, you would want to write your final moment of inertia in terms of m full. But if they just start you out with this piece and they tell you, we have this piece, its mass is m, well then this is the m that they're referring to, this ml as I called it. So be very careful when reading the question and understand what the m refers to. Do they give you a full cylinder and tell you that its mass is m, or do they give you this hollowed out cylinder and tell you that its mass is m, and then express your answer, of course, in terms of m and r? You want to make sure that it's in terms of the m and r, specifically the one that they give you. So be very, very, very careful about that. I would recommend just redoing this problem, say after, give yourself 3 days to kind of forget parts of the solution and see if you can do it again. And then, what do I always say? 3 days, half a week, and then do it one more time after like 1 week, and maybe one more time after 2 to 3 weeks. And if you've got it at that point, then I would say that you are in good hands. So yeah, I would definitely recommend revisiting this one. Do not sleep on it. Make sure you understand it, and maybe also ask yourself, do it in terms of each of the cylinders, in terms of each of these m's, and in terms of each of these r's. Just do it all 3 possible ways so you've covered all your bases. That is a parallel axis theorem covered. Now we need to go over one more little thing that I promised to cover, which is just a little bit of math to convince us that moving away from the center of mass will always be an increase and not a decrease. Because some people might be worried that, if I'm starting at the center of mass and, the farthest pieces of this thing, the farthest masses are equally distant, but then I move away from the center of mass. Sure, I'm moving farther away from some parts of it, but I'm moving closer to the others. So doesn't that balance out? Doesn't that make up for it? The answer is no, because the distance in our moment of inertia formula is squared, and that squaring is what makes it guaranteed that the minimum can only occur for an axis through the center of mass. So let me see how I want to go about this. Let's start on the back side of this page, and let's take a simple object like a rod, because we haven't gotten tired of looking at rods today, have we? And let's start through an axis through the center, or with an axis through the center, I should say. And let's chop this up into a bunch of little pieces. Let's chop this up into, how many can I get here? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, perfect. Doesn't even matter what units of distance we use here. I'm just going to keep it unitless. So in this scenario, we have, if I were to treat them as a bunch of point masses, I can just use their centers of mass. I can replace them with points at their centers of mass instead. And we'll say that these 2 points are at a distance of 1. So this is a distance of 1, and this is a distance of 1. These next 2 points are at a distance of 2. Well, technically, I guess it would be, yeah, well, no, I guess it would be a distance of 3. So these next 2 points are a distance of 3 away. And the next pair of points, wait, that's not 3. 3 is from here to here. Forget what I said there and there. This distance is 3. This next distance is 5. This next distance is 7, and so on. So what happens if I move to another axis? What happens if I move just 1 step? What happens if I move just 1 step to the right or to the left? Let me draw this thing again. I'll try and draw it below here so that we can kind of visually compare them a little bit better. If they're right underneath each other, it should make the comparison easier. Let's say I shift this 1 step to, let's do the left since it's a little bit less crowded there. And I know I don't have to be super precise with this, but trying to get things to line up at the bare minimum. Okay. And draw my new axis. I'll do it in a different color. Let's do orange. If I move to this new axis over here, for example, let's see what we have. So if each of these pieces has a mass, we'll call it little m, then what I would have for the total moment of inertia for this original axis is little m times 1 squared plus another little m times 1 squared, so little m times 1 squared plus 1 squared, and then plus these 2 pieces would be 3 squared and 3 squared. And then we'd have 5 and 5 squared. And then 7 and 7 and 9 and 9 and 11 and 11. 7 squared. Getting ahead of myself. 7 squared plus another 7 squared. 9 squared and another 9 squared. And then 11 squared and another 11 squared. So that is what we have to begin with. Now we shift over to here. And if we shift 1 space like this, then now we have pretty much an identical scenario up to, let's see, 1, 2, 3, 4, 5. Up to 5 pieces. Here we're going to see something new. So for these first 5 pieces, we've got 1 squared and 1 squared, and 3 squared and 3 squared, and 5 squared and 5 squared. So those first 5 numbers are still going to be the same. 1 squared and 1 squared for those 2 sides, and then 3 and 3, 5 and 5, and 7 and 7, and 9 and 9. That so far is the same. But now we have these 2 pieces. This one is at 11 and this one is at 13. So now we've got a piece at 11 squared and another piece at 13 squared. Well, let's compare and see what just happened. So up to here, the sums have been identical. But now we have done what? We have introduced, basically, we got rid of an 11 squared, and in its place, we added a 13 squared. We subtracted 2 units of distance from one side and added them to the other side. And while the total distance is still, what, 22 from one end to one end, 11 on one side and 11 on the other. Over here it's 5 on one side and 6 on the other. 1, 2, 3, 4, 5, 6, 7. Oh, wait, how many pieces do I have? Oh, I have 12, right, because I chopped them equally. So I have, let me gather my thoughts for a second. My brain isn't keeping up with my mouth, or maybe it's the other way around. So we had, let me gather my thoughts. I don't even remember what I was trying to say. Oh, goodness. Maybe I do have ADHD, who knows? Not that it's going to change what I'm going to do with myself. I'm not going to rely on pills. Why am I blanking so hard? My mind just went completely blank right there. We were saying, let me walk back through my steps. So we've got 6 pieces on either side of this thing, equally spaced. Over here, we now have 5 pieces on this side and 7 pieces on this side. So essentially what we've done is we've taken what would have been the 6th piece on this side, and we have moved it and attached it here, is essentially what we did. So we lost an 11 squared, and what we got for it was a 13 squared. So the total number of pieces hasn't changed. The sum of the distances of the pieces hasn't changed, but the sum of their squares has. We have gained 13 squared minus 11 squared worth of additional moment of inertia here. We've gained 13 squared minus 11 squared, which is 169 minus 121. 13 times 13 is 169, right? 13 squared. Okay. I don't know why, but it looked weird to me for a second there. It's kind of like that feeling when you really stop to think about a word that you've been using all your life, and then you stop and think about the way it's pronounced, and you go, that sounds wrong, even though you know it's the right word that you've been using all your life. But yeah, hopefully this demonstrates to you that no matter what you do, if you move the axis away from the center of mass, you're always going to get an increase. Whatever decrease you get on one side, the increase that happens on the other side will always outweigh whatever that decrease is. You could try this with even smaller shifts of the axis. You could try shifting this axis 1/10 of the distance that I did here, or 1/100th of it, and so on and so forth. It won't matter. If you do, let me think here. How would I write this in a way that just focuses on the pieces that don't change? or rather that just focuses on the pieces that do, is what I'm trying to say. So I would do, let's see, if the axis shifts by a distance d, I'll call it lowercase d here, if the axis shifts by a distance d, then you basically lose a piece from one end, you lose I guess you could call it L over 2 minus d squared, and gain L over 2 plus d squared. I know this might be confusing to some of you, but I'm still trying to think it through before I try and explain it. L over 2 minus d squared and L over 2 plus d squared. And then if I calculate the difference between those two, L over 2 plus d squared minus L over 2 minus d squared, then what I get is L squared over 4 plus LD plus d squared minus L squared over 4 minus LD plus d squared over here. That cancels out. D squared cancels out. LD minus negative LD is 2LD. So the net gain is you get 2LD more moment of inertia. Okay, so let me now explain what I just reasoned through with myself. So if we start with a rod of length L, and we have its moment of inertia through its center of mass, whatever it is, and we chop off d worth. If we chop off d worth of material over here, and we add it onto here, and we add it onto here. So we add this on here, and we subtract this off of here. That's essentially the same as shifting the axis by d units to the left. Then what we've done is, originally this thing was, well, maybe not exactly at L over 2, but close enough. This distance is L over 2, and this distance is L over 2. Whoops, right there, stop it right there. So that's also L over 2. So what we've done is we've removed a piece that is approximately at a distance of L over 2 minus d away from the axis of rotation. We've removed something that is L over 2 minus d away, and it has some mass little m. So we lost little m times its distance from the axis is L over 2 minus d. This L over 2 minus d. Technically, it's L over 2 minus 1/2 d, right? Because it's supposed to be over here and not over here, but close enough. And actually, if you just change this to 1/2 d, you're still going to get pretty much the same result. When you square the 1/2 d over here, you're going to get 1/4 d squared over here, and that's going to cancel out. And I suppose you're going to just have a 1/2 over here. So, okay, actually, yeah, we can do that, fine. And then there's a 1/2 over here, and that will cancel with the 2, so you get LD is the net increase. I'm getting ahead of myself. So L over 2 minus 1/2 d, or minus d over 2, in other words, is what happens over here. That's going to be this distance. Okay, let me redraw it over here. Yeah, that is L over 2 minus d over 2. This right here is L over 2 minus d over 2. That's probably too tiny to read, but at least you can tell from hearing me what it's supposed to say. And over here, we are adding a piece at a distance of L over 2 plus d over 2. Over here, we're adding a piece at position L over 2 plus d over 2. So whatever the mass of that piece is, times L over 2 minus d over 2 squared, that's how much moment of inertia we lost by removing it from this end, and then the moment of inertia that we gain by attaching it to this end would be m times L over 2 plus d over 2 all squared. And then if we take how much we gained minus how much we lost, overall we gain an amount LD. Not something that you actually need to know for the AP exam, but I got hooked. I got in the grip of things and decided to just pursue it to the end. And now I have a new thing to teach my students from this year onward. See, this is how you get better at physics, ladies and gentlemen. You just witnessed it happening in real time. I've gone for how many years without ever actually doing this calculation, and I just now sat down and did it. So now I have something new to teach, and now I have a better understanding. The secret to getting good at physics is to keep on doing it for years and years and years after your last physics course ended. It's not about intelligence, it's about sticking to it. My chemistry back in high school was way better than my physics, I can tell you that much. Don't think I was born some sort of naturally skilled physicist. My skill set was more suited to chemistry than anything else. But anyway, now that we have hopefully sufficiently proven that whatever distance d you shift the axis by, you're always going to have some sort of gain in moment of inertia. Now, hopefully, we can start moving on to... What do I want to move on to? That is a good question. Let me see what I wrote in the description of this. Give me a second. I want to open a new tab and look at what I wrote in the description for this. Okay, parallel axis theorem we did. And I said if time allows, we will introduce rotational kinetic energy and see how moment of inertia can affect the energy of an object. We probably won't do that today because we're already at 3 hours. So here's what I'm gonna do instead. Let's do a couple of problems where we take advantage of net torque equals I times moment of inertia, or moment of inertia times angular acceleration, rather. Let's take a look at a problem or two involving that, and we will dig into rotational kinetic energy next time. Yeah, that's what I'll do. So give me a minute to find some problems. That one I already did in a different video, so I don't need to repeat it. Okay, let's look at this one. Let's start with a fresh new sheet, and I see it's starting to get a little dark. I mean, it's still pretty bright outside, but with the direction my window is facing, I'm not getting direct sunlight anymore. Let me flip on these lights. Let's see. So we have a cylindrical fishing reel. Has a moment of inertia 6.8 times 10 to the negative 4 kilograms. It says we have a cylindrical fishing reel. A cylindrical fishing reel. It's going to be shaped something like this, cylinder shaped. Has a moment of inertia 6.8 times 10 to the negative 4 kilogram meters squared. So I equals 6.8 times 10 to the negative 4. Really small moment of inertia on this one, which I guess makes sense. Fishing reels aren't that big in radius and probably aren't that heavy in terms of mass either. So 6.8 times 10 to the negative 4 kilogram meters squared. And it has a radius of 4 centimeters. Well, there you go. They told us radius equals 4 centimeters, or as I will convert it to 0.04 meters. A friction clutch in the reel exerts a restraining torque of 1.3 Newton meters if a fish pulls on the line. So we'll just call that a frictional torque. The fisherman gets a bite, and the reel begins to spin with an angular acceleration of 66 radians per second squared. What is the force exerted by the fish on the line, and how much line unwinds in 0.5 seconds? So they said torque restraining, or torque friction is what I will call it, is 1.3 Newton meters. And the angular acceleration of the reel is 66 radians per second squared. So the formula we're going to use, net torque equals I alpha, that formula requires your angular acceleration to be in radians. You can't have it in degrees or revolutions. If that's what you get, you need to convert. I talked about this whenever it was that we first talked about degrees and revolutions. What was it, 2-3 streams ago? I don't even remember at this point. So they want the force exerted by the fish on the line. So force fish, which is, I guess, the force of tension in the line. And they want how much line unwinds in 0.5 seconds. So in other words, they want the length of line unwinded where t equals 0.5 seconds. Okay, let me go ahead and draw the rest of this fishing rod. Not that we have to fully draw a fishing rod, but there's going to be some line over here. I guess, which side would it be tied to? I guess the line would come out of this side. And then there's going to be a fish in the water. And it's really upset about getting caught, and it's pulling on the line, and it's creating some sort of tension that ultimately ends up pulling with some force on the reel over here. So there's going to be some force of tension over here due to the fish pulling. That's what they're asking us to calculate. And as the reel unwinds, it does end up unwinding. It does end up moving. I guess in my drawing it would be clockwise. So there's a clutch that helps prevent it from unwinding too fast. Just gives you a little bit of an advantage as the fisherman to try and catch this fish, and it's going to create an opposing torque. It's going to create a counterclockwise torque of 1.3 Newton meters. So we need to figure out what the tension force is. So if we know the moment of inertia and we know the angular acceleration, well then we know what the net torque is. The net torque, we've got two forces over here creating torque. We've got the friction torque and we've got the tension torque. I'm going to say clockwise is the positive direction here because that's the direction that the fishing reel is unwinding. I'd rather have the direction where things are already moving be the positive direction. Just makes things easier, in my mind at least. So I'm going to say torque due to tension minus torque due to friction is going to be my net torque. My tension force over here is going to pull on the edge of the reel, and that's going to cause clockwise rotation. You could figure that out just through process of elimination here, since the tension torque has to be what causes this thing to move. It certainly wouldn't be the friction torque that's causing it to move forward after all, and that's equal to moment of inertia times angular acceleration. Now, some of you might be saying, well, wait a minute, what about gravity? Isn't gravity acting on the fishing reel? Well, yes, but it's not generating a torque. Because if the thing is already rotating, we don't get to choose the axis of rotation. This is not an equilibrium problem. This is the first new thing that we have to get used to. If the net torque is anything other than zero, we have to make sure we know what the axis of rotation is. We don't get to choose it. The axis of rotation has to be just the axle of the reel, which is in the center. Okay, well, where does the force of gravity act on an object? At the center of gravity. So the force of gravity acts at your pivot point, so the torque from it has to be zero. Torque due to gravity must be zero. Tension, on the other hand, acts on the rim of this reel, and that is going to be at a pivotal displacement of 1 radius away from the axle. I forgot to label this as tension force. And then we don't really see where the friction force happens, but I would imagine it's somewhere over here. So there's probably like this it's the little button thing on a fishing rod that you press, and when you press it inward, it presses against the reel and grinds against it, and that causes friction that slows it down. The mechanism might be more complicated than what I'm describing, but that's basically it. Now, we don't have to do force of friction times R times sine of 90 degrees here because they already did that for us. They told us it was 1.3, but just for the sake of having a complete diagram, there you go. And I suppose for the rest of the forces, it would be the fisherman holding the rod, and that should give you whatever remaining force you need to balance out these forces so that the net force is zero, even though the net torque is not. the fishing rod itself as a whole needs to sit still, but its reel needs to be able to unwind. So you need a non-zero net torque, but a zero or at least nearly zero net force, because chances are the fisherman is going to get up and, move around a little bit, and the rod, even if they don't move around, if they just hold the rod still, it's still going to shake a little bit in their hand. So details. So torque due to tension is going to be just R times tension force times, it'll be sine of 90 degrees. If the tension acts tangent to the reel, which it should, because, it's just wound around the reel, then, yeah, the distance from the axis of the reel to the point where the tension is actually being applied at any given moment should be 90 degrees. So that'll just be a 1, and then minus 1.3 equals 6.8 times 10 to the negative 4 for moment of inertia times 66 radians per second squared for angular acceleration. R was 0.04, so I'll go ahead and substitute that as well. And I'll add the 1.3, so 0.04 times force of tension equals whatever this is plus 1.3, so 6.8 times 10 to the negative 4 times 66 is 0.04488, and then add 1.3 to that, and I get 1.34488. I'll keep all of those digits this time around. 1.34488. And divide by 0.04, and this is probably where I'm going to round. Or maybe not, 33.622. Force of tension is 33.622 newtons. Alright, that's how much force the fish is exerting. And then how much length unwinds. This is just a rotational kinematics question. The fishing reel starts from rest, so omega initial is 0. And we have the angular acceleration, and we have the time. So we can just do second equation, I believe. Delta theta equals omega initial times t, which is just going to be 0 since omega initial is 0, plus 1/2 alpha t squared. 1/2 of 66 is 33. 33 times 0.5 squared, that's 33 over 4, which is 8 1/4. Delta theta equals 8.25 radians, and then multiply by the radius, multiply by 0.04, and that will give you the arc length. That's what this L is supposed to be. The length of fishing line that went out is 8.25 radians worth. So that's 8.25 times 0.04 is 0.33 meters of fishing line. That sounds realistic to me. So L equals S equals R delta theta equals 0.04 times 8.25 equals 0.33 meters. I didn't have to round anything in this problem. I mean, I could have chosen to, but I'm glad I didn't. Okay, let's pick one more and wrap up with it. Okay, here's a good one. At least good enough for our purposes. Something quick and simple that gets you a bit comfortable using our new equation. It says a 150 kilogram merry-go-round in the shape of a uniform solid horizontal disc of radius 1.5 meters is set in motion by wrapping a rope about the rim of the disc and pulling on the rope. I lost my place in... Oh, there it is. What constant force must be exerted on the rope to bring the merry-go-round from rest to an angular speed of 0.5 revolutions per second in 2 seconds? So very much like what happened in the force chapter, kinematics is sometimes being used to get your acceleration, or in this case, angular acceleration, in order to solve the torque part of the problem. Net torque equals I alpha is your bridge between torque and rotational kinematics questions, basically. The same way that net force equals ma was your bridge between regular kinematics and force. So 100, let me draw the thing first. So it's going to be a disc, basically. Rotated through its center. Radius was, how much did it say? 1.5 meters. 1.5 meters. Its mass was 150 kilograms. Set in motion by wrapping a rope about the rim of the disc and pulling on the rope. What constant force must be exerted on the rope to bring the merry-go-round from rest to an angular speed of 0.5 revolutions per second in 2 seconds? So omega initial is 0, omega final is 0.5 revolutions per second. Time is 2 seconds. I'm going to say that it's going to be rotated this way. There's going to be some sort of, I guess, rope that's being pulled on like this along the rim of the merry-go-round, and whoever's pulling on this rope is also rotating with the merry-go-round so that the direction of the tension is always tangent to the edge. Was there anything else I needed from here? Nope, it's just asking what constant force is needed here. So, book problems will sometimes expect you to know the moment of inertia formulas, or at the very least, because it's a book problem and you by definition would have to have the book, you can just go in the book and go to whatever page has those formulas in it and just use that as reference. If you forget the moment of inertia formulas, you will probably be doing the disk a lot. 1/2 mr squared. I mentioned it before as one of the ones that might be worth memorizing, even if you're not required to memorize it. So I disk through its central axis at the very least. I disk through center or cylinder is going to be 1/2 mr squared. I cylinder, I'll just abbreviate it, is 1/2 mr squared when the axis of rotation goes through its center. So we can take its mass and radius and use that to calculate its moment of inertia. which we will need later, together with angular acceleration to figure out the net torque required, and once we know the net torque required, we can calculate the tension force required. Okay. So kinematics first. I want to convert from revolutions to radians, so I can do 1 revolution is equal to 2 pi radians. That cancels revolutions and gets me radians over seconds. So 2 pi times 0.5 is 1 pi radians per second. Now we can do, which equation do I want to use? Just first equation looks like it'll do. So omega final, which is pi, equals omega initial, which is 0, plus alpha times t. So just divide by 2. Angular acceleration is pi over 2. This is why you hold off on substituting pi. Look at how simple that is. Pi over 2, and that's going to be in radians per second squared. I didn't leave enough room for it up there. So we're going to use that. We're going to say net torque is equal to, well, there's a force of gravity and a normal force acting on this, but they're both acting at the axis of this merry-go-round, so they're not going to create any torques on this thing. And we're going to assume that there is no friction on the axle because we weren't told anything about friction, although you might see situations where the axle has friction. So let me go ahead and unwind this just to visually illustrate what I'm even talking about. So yeah, this thing, this little metal piece over here, this axle, it might rub against the rest of the wheel, disc, whatever it is that's rotating, and that can cause some friction that can slow things down. As you see, it's not at the center, it's very close to the center, but not at the center. So this friction force can exert some torque, however small it may be. Can exert some sort of resistive torque. So keep that in mind. Sometimes friction from the axle will factor into your torque formula, but usually we just assume the axle bearings, whatever the problem calls them, is frictionless unless we're told otherwise. So the only force left that's going to create a torque here is the tension. So force of tension times, well, the tension force is applied at this point, which is 1.5 meters away from the axis of rotation. So it's going to be 1.5 times force of tension times the angle here is going to be 90 degrees because the tension is tangent to this disc and the radius is going to be perpendicular to the tangent at all points. So 1.5 force of tension times sine of 90 degrees. I'm sure some of you are sick of having to write the sine of 90 degrees, but I already said last time, it's good to establish this as a habit so that you don't forget it when it actually does matter. So that's going to be all the torque that we get from our forces, and that has to also equal the moment of inertia times the angular acceleration, which we now know is pi over 2 in radians per second squared. Okay, moment of inertia. Let's figure you out. For a disk or cylinder, it's 1/2 mr squared, assuming it's rotated through its central axis, which it is. So that's going to be 1/2 I of the merry-go-round is going to be 1/2 of 150 times 1.5 squared. That's going to be 1/2 of 150 is 75 times 2.25. 75 times 2.25 is 168.75. 168.75 kilogram meters squared. And if we sub that into here, we should be able to solve for the tension. Actually, I could have just skipped on one of those 1.5s. Because if I plugged in 1/2 times 150 times 1.5 squared here, I could have canceled the 1.5 over there. But, oh well, missed opportunity. We'll get to see an expression problem or two eventually, I'm sure, where we can play around with canceling some of these R's and seeing what we can do. We can find some problems where the radius isn't going to matter at all. That's coming, but not today. So 168.75 times pi over 2 divided by 1.5. I'm going to go ahead and divide by 1.5, and that gets me 112.5 for this, and then divided by 2 is 56.25. So that's dividing by the 2 from here. So that leaves me with 56.25 pi. Force of tension equals 56.25 pi newtons, which, if I plug in the value of pi now, is about 176.71. About 176.71 newtons of tension. All right, so there is one more little thing that I wanted to talk about when it comes to point masses before we wrap up. And I did kind of talk about it last time when we brought up moment of inertia. I talked about how you can treat any object as a point mass as long as the size of the object is small in comparison to its distance from its axis of rotation. So I just wanted to remind you of that because we didn't really get the opportunity to play with that today, but it'll come up soon enough, so I figured I should reinforce that point here. So your clues to look for that is if the axis of rotation doesn't go through the object to begin with, if the axis of rotation is out of the object, so that's one, and two, it has to be significantly far away from the object. So if I had something like a cylinder over here, and I'm getting its moment of inertia around this axis, not that they would actually ask you this because it would be, well, actually, no, we could do this with parallel axis theorem now. Yeah. If this distance over here is not that much bigger than the radius of the cylinder, then you would have to use parallel axis theorem on this. But if you had, say, an axis of rotation like this, and you had your cylinder or sphere or whatever object all the way out here, well, maybe this is still not a big enough scale, but I hope you're seeing the big picture. I know I already mentioned it last time, but it bears repeating. If this distance is very, very, very large in comparison to this distance, and I guess that kind of depends on your best judgment in some situations. if the distance to the axis is very large in comparison to the size of the object, then you can treat the whole object as a point mass, and it'll be a pretty decent approximation. The larger the scale, the better the approximation. I say this because I want you for homework to get the moment of inertia of an object in uniform circular motion. And actually, wait. What more could I even do with that as a homework problem? Let me think this through for a second. Well, maybe more than a second. No, I guess that would have to wait until we do rotational kinetic energy. Okay, never mind what I was going to say. So instead for homework, what I'm going to recommend is just look for more problems like this involving net torque and angular acceleration and moment of inertia. We'll just stick to these for now. Just look for that in your textbook if you have your own, or in the OpenStax textbook linked in our course plan. If you don't have a textbook of your own, let me go ahead and go to that screen real quick. So in the course plan, in case you're new here, this is linked in the description. If you click this over here, it will take you to a website where you can download this book. And in this book, if you go to, where is it? Statics and Torque, and you go down to conceptual questions and problems and exercises, I do have some that I recommended. If you go back to this page and you open up rotational kinematics and dynamics, you should see some recommended practice questions. So that's what I would look for, any of the ones that involve topics that we've already covered. Go ahead and practice with those. And also look at some worked examples. I do always put some of those in there as well. And I guess what you're looking for this time would come from this second batch of worked examples. You see that first batch over there, that's just like basic torque problems with equilibrium stuff, but we're past that now. We're looking at more of this stuff. So yeah, I would look through this playlist and see if there's anything in there that would serve as good practice that still just relies on the stuff we've covered so far and doesn't really require you to know anything past this point. And next time we will just cover some of the remaining topics. Rotational kinetic energy. I imagine I'm going to do several problems involving that. Maybe we can squeeze in angular momentum, but I'm not entirely sure about that. That's not a promise, but at the bare minimum, we will look at rotational kinetic energy and do some energy problems at the bare minimum. And we'll probably also talk about things like rolling without slipping. So that is what you can expect next time. And next time will hopefully be sometime tomorrow, but that is still up in the air. It's not guaranteed. So if it ends up disappearing off the schedule, or more likely shifting to another day, that's just what happens. Anyway, that'll be it for today. Hope you learned a lot. Until next time, class dismissed.